Hello, you're welcome to Master T Math class. Here, we want to consider this topic in mathematics, which is circle geometry. Now, let's look at some important things here before we look at some theorem. Number one, we have a chord subtends two angles at the center of a circle, two angles at the center of a circle. So when we have a circle here, let's have the circle with center hole here. And let's say we have a chord labeled as AB. This chord AB can subtend two angles at this center here. So we connect A to O and also B to O. That is, this angle at the center here, we have the one inside, which is the obtuse angle AOB. And also we have the one outside here, which is the reflex angle AOB. So these two angles are formed. So the word subtend here is another word for that is forms. So this angle formed at the center here, we have two of it, two angles. That is the obtuse one and the reflex one there. And also we need to understand that a chord can also subtend angle at circumference. A chord subtends two angles at the circumference of a circle. That is, now when we have a circle, we have this circle with center O. Now let's say we have a chord. We call it chord AB as well. Then it implies that this chord here can subtend angle at the circumference at this side. And we can call this point C. That is, we have angle ACB. This angle at the circumference. And also it can subtend angle at this side as well, at the circumference. And when we label this as D, also we have angle ADB at the circumference at this side. So these are ways that a chord can subtend angle. And sometimes it might not be a chord, it might be an arc. So we might say or an arc. Or an arc. So instead of a chord, we can use instead of chord, we can use an arc as well. That is, if this line is not there, this chord is not there, we can consider AB here as arc AB. So it's either we are talking about a chord or an arc. So, and this here, we are using a chord. So a chord can form angle at the center and also can form angle at the circumference. So this is very important for us to take notes. And next, let's look at number one theorem. We have already proved that theorem in our previous classes. And again, you can still prove it again for better understanding. That is, the theorem, we label it as Theorem 1 here. Theorem 1. And this theorem states that the angle subtended by a chord, the angle subtended by a chord or an arc at the center of a circle is twice that which a chord or arc subtended at the circumference of the circle. At the circumference of the circle. So this is theorem 1. Now let's look at some keywords in this theorem. We have a chord, that is, from a circle center hole, we have a chord from a circle center hole, and the angle formed at the center by the chord or an arc is twice that which. So this word as well is a keyword, twice. So the angle that is formed at the center is twice that which the chord and arc subtend at the circumference. So we also have the angle at the circumference here by the same chord. Now let's consider the proof here. So to prove the theorem, the first thing is that we should list out what is given on the theorem. So what are we given? First, we have a circle center O. So as we are writing what is given, we can demonstrate it by drawing the diagram. So let's have the diagram at this side, and we have this as a circle with center O here. Then the next thing here is that we have a chord or an arc. Here, let's consider it as a chord, and let's label that chord as AB, a chord AB. So we can come to this circle here, and we draw this as a chord, and we label it as AB. Then also from the question, we discover that we have angle at the center. The angle subtended by a chord or an arc at the center of a circle. So this chord here form angle at the center. We have looked at that this chord can form angle at the center here. And here we have two angles. And here we also consider this obtuse angle AOB. So now that means next one we want to say that we have obtuse angle AOB at the center. And also number 4 is also talking about the angle at the circumference. So it's twice that which is obtained at the circumference. Now we can also say we have angle, we can use any letter, angle ACB at the circumference. We can shorten circumference like this. So now this chord also subtend this angle at the circumference. So we can join it back to this point B so that it is formed by this chord AB, and we label this as C. So we have therefore angle ACB at the circumference. Now from the theorem, what is required to prove? Required now to prove that the angle at the center by the chord is twice the angle at circumference. That means to prove that angle AOB is equals to twice means 2 times angle ACB, which is angle at the circumference. So that's what we are proving from the theorem. Now, here we need to do a construction. So now we say construction construction. Now we want to join C to O. Join C to O and extend to, let's say, point D. So now we want to connect this point C to point O and extend it to a point D. So we can use a construction line, dotted line, then label this point as point D. Then now to prove proper now, let's look at the proof properly. Now we want to consider this triangle here, which is triangle AOC. When we look at that triangle AOC, we discover that from the center to this point A, that's center to the circumference, is a radius, and also center to the circumference here is also a radius. So we have, therefore, line AO is equals to line CO. Why? We have, that is, we can say that here in triangle AOC, line AO is equals to line CO. That makes two sides equal. And you know, when we have two sides equal in any triangle, that triangle is called an isosceles triangle. So triangle AOC now is an isosceles triangle. And one of the properties of an isosceles triangle is that the two sides are equal. That's number one. And also the base angle. And don't forget that the third side is the base, and this is the base angle. So the base angle here are also equal. Now let's label this as CAO. So we have, therefore, angle CAO is also equals to angle ACO. That's angle ACO. And let's use it as letter X. So we put letter X here and also letter X here. That's base angle of an isosceles triangle are equal. Then we can put it like that, that is base angle of isosceles triangle. Okay, now what next? We also have this triangle extended. When the triangle is extended, like let's say we have this triangle, the way we have it here, we have this side extended like this, and you know, this is X here, this is X here, and the exterior angle here of any triangle is the sum of the two opposite interior angle. So that means here this angle will be x plus x, which is 2x. So the same way we can get this angle here, which is angle AOD. It will now be x plus x, which is going to be 2x. Then we can put it down here and say also angle AOD is equals to x plus x, which is 2x. Why? That's exterior. We put the reason as exterior angle of triangle AOC. Now, we are done with this side now. Similarly, we consider the other triangle, which is triangle BOC. So we can say that similarly here, in triangle BOC, in triangle BOC, we have two sides equal, which is line BO is equals to line BO is equals to line CO. Now, also both are radii of semicircle, and which make this triangle also to be an isosceles triangle. And in the same way, we have the base angle here are also equal, which when we label it, we can say angle CBO. So we have angle CBO is also equals to angle BCO. BCO. And we can call it letter Y. So if this is Y, it means this is also Y. That's property of an isosceles triangle. That's base angle of an isosceles triangle. And One thing here now is that we also follow what we have here. This side is also extended in this triangle BCO. So this side is extended and we can get this angle as well, which is also the exterior angle. It's now going to be y plus y, which is 2y. So in the same way, we can say that angle BOD is also equals to y plus y, which is 2y. That's also exterior angle of triangle BOC. All right. Now, let's conclude now. To conclude in this theory, conclusion. So, conclusion now, we should look at this angle at the center. The totality of this angle at the center is what we have here. Now, that this angle AOB now is now 2x plus 2y. That is, here we can say that angle AOB at the center is now equals to 2x plus 2y. And don't forget that here we can say angle AOB now is equals to 2 is common here. We factor it out and we have 2 into bracket x plus y. Then let's look at the angle at circumference as well, which is this total angle here. That's angle ACB. It's also x plus y. That is, we can say note, but here we have angle ACB is equals to x plus y. So that's angle at the what? Circumference. So now, instead of writing plus y here, we can simply write ACB. So therefore, we say angle AOB is equals to 2 times angle ACB. So therefore, the required here has been proved. So here we have proved this theorem. So this theorem one is the foundation of this particular topic, which is cycle theorem. So once we are able to prove this theorem and know it properly, so all other theorems will follow this. And with that, we are going to be able to solve questions on the cycle theorem. So you are watching live class at Master T Math class. So do it to support us here and share this video. Also, if you are just joining for the first time, you can subscribe to this channel so that you won't miss out on our uploads, and also give a thumbs up to this video. So now let's look at a question here that follows this theorem one exactly. So we want to apply this theorem one before we look at the second theorem in this class. So here, let's consider this as the example that follows this theorem. So here, we are given this circle. So we have this circle given as a center over here. Then here we have the center, and this angle at center is given to be 130 degrees. So here, this angle is at the circumference, and this point is labeled as A, this is B, and this is C. And we are given this angle here to be 26 degrees. And here there is a line, like a construction line, that join this point C to O and extended. And something like this is also put here. So this is just a distraction. And the question says, one, find one, the value of angle CBO, and also two, angle BOC. So we are finding two angles here. BCBO. So we should know which angle we are finding. When we have three letters this way, CBO, it means that the one at the center here is a reference point. So it's like we have between CB and BO. So B is common. You understand? So between line CB and line BO, which means that you can say that you have from CB then to BO. So this angle, so we are finding. Then in the same way, angle BOC. So angle BOC, when we break it down, you have BO and OC. So you look at that line, BO and OC. So in between here, you are looking for these two angles. Now, first thing that will come to our mind that if this is the center of the circle, from theorem 1 that we have, the angle at the center here is twice the angle at the circumference. So now we can say that 130 degrees is equals to 2 times angle ACB. So that's what we prove from first theorem, that the angle at center is twice the angle at circumference, and the angle at circumference here is angle ACB. So now that is what we have. Okay, now let's get ACB now by dividing this side by 2. Also divide this side by 2. That these two cancel each other here. We have angle ACB left. So we can say that angle ACB is equals to 130 over 2, which is 65 degrees, right? Now, let's keep this first. And also, looking at this diagram from here, we discover that we have a triangle here, which triangle AOC. And we can say from triangle AOC, looking at that, we have AO is a radius. So line AO is equals to line CO, because why? Both are radii or same circle. So both are equal. And you know, when two sides are equal here, it makes that triangle to be isosceles. So therefore, triangle AOC is an isosceles triangle, right? Now, why? Two sides are equal, which implies that the base angle is also equal. So this angle is also equal to this angle. So this is 26, this angle is also 26. So we can say that angle ACO, angle ACO is now equals to 26 degrees. Why? That's base angle of isosceles triangle AOC, alright? Okay. Then there is something interesting here. We got ACB to be 65, which is everything here, and this side is 26. So easily we can get only this angle, which is angle BCO. So how do we get that? We can say angle BCO now is now equals to 65 degrees minus 26 degrees. Of course, this will give us 39 degrees. So this angle only here is now 39 degrees, right? Then we are finding angle, which is angle CBO. So looking at this triangle BOC, also triangle BOC is an isosceles triangle. Is an isosceles triangle. Why? BO is equals to CO. Y, radii or semicircle. So this triangle BOC is also an isosceles triangle because BO and CO are equal. Therefore, the base angle are also equal. This is 39, this is also 39 degrees. And therefore here, question 1 now, we have angle CBO that we are finding is now equals to 39 degrees. That's base angle of isosceles triangle BOC. So that is the first one. Then the second one, angle BOC here. Angle BOC here, it's the third angle of triangle BOC. So when we have sum of angle in the triangle, which is 180 degrees, so that means we can subtract the sum of these two angles from 180 degrees, and we have angle BOC now is now equals to 180 degrees minus the sum of these two angles, 39 plus 39, that gives us 78 degrees. And here now we have this angle to be 102 degrees. So here is a direct application of the theorem 1. So once we are able to prove that theorem, we can solve this question without stress. Okay. Now, before we look at some other examples, let's look at theorem 2 in this class. And then the proof of that theorem 2 is directly from theorem 1. And what is that theorem 2 saying? Theorem 2 is saying that all the angle formed by a chord in a segment are equal. So let's put it down here. That is, we have the second theorem, which we call theorem 2 here, is that all the angles subtended by a chord in the same segments in the same segments of a circle are equal. So that is it. We have also a chord here, and sometimes you might also refer to it as an arc. So it's either we are talking about a chord. Now, all the angles subtended by a chord in the same segment. Now, let's look at this in a diagram briefly. So let's say we have this as a circle, which is centered at O here. And let's consider this as a chord, and we refer this as a chord AB. Now, this chord AB divide this into two segments. We have the minor and the major segment. Now, all the angles that we form by this chord in a segment are equal. Now, let's look at this. This chord can form this angle. It can form this angle here. That is, it means if this is C here, we have angle ACB formed by this chord. And we can also form another angle as many as possible. So we can say if we have this angle here formed by this chord, here we can call this angle D, and also we can have another one. It depends on how many we want there or how many we are given. So here, this is also formed by AB. So we can label this as E here. So all these angles are in the same segment at the circumference. So it is formed by this same chord. That's what is important. And the theorem is saying that these angles here are therefore equal. Why are they equal? It follows from theorem 1. Now, the proof of that theorem, we can join center to point A, that's the junction line. Also join center to point B. And you should discover that this angle now is the angle at the center. And you know that angle at center is always twice the angle at circumference. So let's pick any of these angle first as angle at circumference. So if angle is the circumference here, let's say is x, it implies that since angle at center is twice, angle at center here will be 2x. And this is 2x at the center. This is at the circumference. It means also it's, directly the angle at the circumference to this. So if it is 2x, this is also expressed to be x. The same thing here. This is at the center. This also at the circumference to this angle. So if it is 2x, this is also x. And when we look at it now, we have x here, x here, x here. So all these angles are now equal. So that's the proof of this theorem. The proof is derived from the theorem 1. So that is that. And also we have another theorem there, which we are going to look at as theorem 3. So that theorem also has its proof from theorem 1. So the theorem states that theorem 3, this states that the angle subtended, or let's put it like this, the angle in a semicircle is right angle, So in another word, we can say that, or the angle subtended by the diameter at the circumference is right angle, and right angle is 90 degree. Why is it semicircle? A diameter already has divided the circle into two equal parts, which is called semicircle. Now let's look at it. If we have a circle here, and this is the center O, don't forget we are talking about a diameter here. So here, the line passing through the center, we call it AB here, is a diameter, and it has divided the circle into two equal parts, which is a semicircle. Now, the angle subtended by this diameter at the circumference. So this angle formed by this diameter now is now right angle. That's the angle 90 degree. So that's what this theorem is talking about. So it doesn't matter how this is drawn. So in as much as the line passes through the center, it makes this a diameter. So yeah, let's have it another way. If the center of the circle and we have the diameter like this passing through the center, and this angle here by the diameter is formed by this side. So this angle here formed by this diameter at the circumference here is of course going to be angle 90 degrees, right angle. So whichever way it is drawn, it's talking about the same thing. So if it is this way, we also have the center. So this is now the diameter, this center O, this center O. So if it is formed Doesn't matter. Once it is formed by this diameter, that is, the angle is coming from these two sides, this angle will be 90. So it is different from when we have something like this. Don't confuse yourself. It's different from when we have something like this. Like you have this as the center, and you have this like is a diameter. So this is center, oh, this is also a diameter. And if I have this angle here and this joint here, this angle cannot be 90 because it's not coming from the two leg of the diameter. One is attached to A, but the other is not attached to B. So we can't call this angle 90 degree. So now, all this will make us to be able to solve riders in circle geometry. When a question is formed and it is combined together with different theorem, so you'll be able to pick those theorem out there and apply it in solving questions. So we have this as theorem 3. Also, we have theorem 4. And for theorem 4, here we shall be looking at the line from the center of a circle to a chord. So it's also an interesting one. So, and the theorem says that the line drawn from the center of a circle to a chord meets at right angle with that chord. So it's important we know that. So the line drawn from the center of a circle is to a chord, right? To a chord is perpendicular. Is perpendicular chord. So this theorem is very, very important. Now let's look at it in the diagram. We look at this as a circle and then with a center hole here. Of course, we have a chord. Let's have a chord AB here. Then the theorem says that the line drawn from the center of a circle to a chord. So let's draw this line from this center now to this chord. What this theorem is saying is that this line here is perpendicular. The word perpendicular means right angle, which is same thing as angle 90 degree. So this now meets at angle 90 degree here. So that is the theorem. That's the theorem. And the proof of this theorem, when we look at this, we discover that when we join this point A to point O, when we connect these two lines with a construction line, and then we join it this way, we discover that here, where this line is meeting this chord, let's label it as N, and we also have the distance from A to N is the distance from B to N. In another way, we can say line AN is equals to line BN. So which make this to be the middle of this particular chord. So if we are finding a length of the chord and we have been able to get AN, we don't need to get BN again. So we just multiply it by 2. For instance, we can say, since they have the same distance, we can say A to N is X and B to N is also X, which makes the length of the chord to now be 2X. So once I've gotten X, I'll just say AB, which is length of chord AB, is now equals to 2X. Now this can be solved. This problem can be solved using Pythagoras theorem. So that is the essence of all those theorems in mathematics. Once you're able to apply it, then you are good to go. Why? Because here We have this as radius, this as radius. Why is it radius? From the center to the circumference. From the center to the circumference. And you know one thing, that here we have, you know, two right angle triangle. Each one are congruent. That is, we have right angle sides. They are both similar, so we can pick any of this right angle triangle and solve. For instance, if the distance from the center has been given, let's bring one out here. We can bring one triangle out. We call this R. We call this center O. We call this N. Distance, if we are given a distance from the center to this chord as say 4 centimeter, and we are given radius as 5 centimeter, we can get x using Pythagoras theorem, and x will be 3 from Pythagoras triple. And if x is equals to 3, then you know that length of the chord AB will now be equals to 2 times 3, which is 6 centimeter. So it depends on the way the question is framed. So once you have the idea that here this form a right angle triangle, which we can apply Pythagoras theorem to, our problem is easier. And this is theorem number 4 in this particular class. So the line drawn from the center of the circle to a chord is perpendicular to the chord. So I believe you are enjoying this class. Why not support us by giving a thumbs up and also share this video so that it will reach those who need it. And then don't forget to subscribe in order not to miss out on our uploads as well. So we are going to be looking at some other theorems as well and solving problem on them. So we have theorem 5, theorem 6, 7, 8, 9. And theorem 5 and 6 are on what is called cyclic quadrilateral. So, and the word cyclic quadrilateral is derived from the word quadrilateral inside a circle. So when we inscribe a quadrilateral inside a circle, we call it a cyclic quadrilateral. So there is two theorems on that. So which we shall be considering when next we meet and solving questions on them. So do well to stay tuned and see you next class. Bye for now.